Welcome back. You've seen now our first full-up example in processing where we did our temperature conversion. We input a value, a temperature in degrees Fahrenheit, and output the equivalent value, equivalent temperature, in degrees Celsius. But we really would rather not program like that, at least using processing, because it's kind of boring. So what we're going to do instead is we're going to explore the graphics capabilities of the processing programming language. It lets us really easily do some neat graphics, interaction, sound, animation. It can capture from your webcam, and so on. So we're going to use those capabilities of the language to try to make this a little bit more interesting and have a little bit more fun with things as we do our programming. Just to show you some of the things we could do, I'm going to give you a few examples here. And these are quick videos, so bear with me if they seem to take a while to pull up. These are on YouTube. And these are things that I've been tinkering with over the past few years using processing. This one is what's called a noise sphere, and it's basically a bunch of supposedly random numbers from a really bad random number generator plot in 3 dimensions with differing colors. And as you can see, they're really not very random at all. And so that's just a way to visualize the quality of a random number generator. And that's an interesting example, very easy to do in processing. Another one of our examples that we like to use is called a Mandelbrot fractal. And a Mandelbrot fractal is a mathematical equation, basically, a fractal, that is always the same. No matter how far you zoom into it, it's self-similar. So this is a little animation showing a Mandelbrot fractal and a zoom on it. As you watch, we zoom in closer and closer to the fractal, and as we pick one of the arms, you'll see that things look very similar as the degree of zoom moves in. Okay? And that's a characteristic of a fractal. And so that's a program, again, written in processing that's pretty easy and makes some very beautiful results. One more fractal example. This is called the burning ship fractal. It's fairly similar to the Mandelbrot fractal, but when you animate it, it looks like a burning ship sailing at you. And in fact, a bunch of them, because again, it's a fractal, so you zoom in on it and things look similar. So as we zoom into these, you'll see the different ships coming up to us and the way they're self-similar. Okay? And obviously there's a ton more that we can do with processing. It's not all about mathematics and visualizing fractals and random number generators and things like that. We can make games, we can do all kinds of neat things. So we need to start though. We need to start someplace. We need to start learning about graphics and processing, and then as we go through the course we'll be able to do more and more interesting and fun things with the language. So let's start talking about how we paint things in processing. Okay, so we're going to imagine that our programs paint onto a virtual canvas, which we call the display window. Usually, not always. You can paint directly to an image, for instance, that you save to a file later on. But generally speaking, we're going to be painting onto the display window. So if you've used a computer, you know about Windows. Either if you're using a Mac or a Windows machine or a Linux machine, you have programs that reside in Windows. Processing, when you run it, will create a window for you called the display window, and we can paint on that. So this painting is done by the computer, and so it happens very quickly, about 60 times every second, give or take, depending on the hardware that you're running and all kinds of other factors. But in any case, painting or rendering of your image happens very quickly. So what we need to know then is, what are the instructions, the statements we can give to the computer to make it paint things on that display window so that we can see them. So for our paint and our canvas, our virtualized paint and canvas, what we paint we can layer just like you would paint with oil paints, so we can draw things on top of each other. We can use paint virtual paint that's either partially or fully transparent, so you can see through it, or you can't see through it. So we can have different levels of opacity with our virtual paint. The canvas that we're using can always be completely erased, so we don't have anything that's permanent. We can get rid of it very quickly. And if we alternate drawing and erasing, remember that the painting happens about 60 times every second. Well, if the image that we draw is slightly different each time, then that image will appear to move. So if you think about a flip book, for instance, where you take a notepad and you draw a ball bouncing, and the ball is at a different location each time or in each page. As you flip the pages, then the ball appears to move. Same thing here. If we make our image move a little bit each time it's drawn and erase the canvas in between, it'll appear as animated. For right now, we're going to stick with stationary, though. So, what do we need to know in order to paint? We need to know where we should paint on the window, on the display window, on the virtual canvas. We need to know what we're going to paint. Is it a shape? Is it an image? Is it a piece of text? Is it a single dot? Whatever, we need to know that. And we need to know what color we're going to use for that particular piece. All right, so let's take a look at some of those examples, or some of those things that we need to know about drawing on our virtual canvas. So first of all, knowing where, we have to understand the processing coordinate system. The canvas that we paint on is actually composed of pixels, which are arranged in a rectangular fashion. So from the dictionary, a pixel is the smallest element of an image that can be individually processed in a video display system. So basically it's a little teeny dot that's on your display window, one of a rectangular grid of dots, and that dot can be individually controlled. Okay? So all in all, our canvas is a big collection of tiny, tiny points, and each point can be manipulated. Each one of those pixels then has a coordinate that's a lot like your Cartesian coordinate system that you would use in geometry. And that coordinate describes the pixel's location. So that's what we're going to use for the where part, is the location of the pixel where we're going to start drawing whatever it is that we're going to draw. Okay, so in geometry you probably used a Cartesian coordinate system like this, where the origin of this plane was right here at 0, 0, and to the left and right we have the x-axis, positive numbers over here, negative numbers over here on the left, and up and down the vertical axis is the y-axis, starts at 0 and goes up, positive numbers, and going down from the origin are negative numbers. Now the processing display window coordinate system is similar but not exactly the same. So basically we have 1/4 of that plane and it's been flopped over. Okay? So our origin in processing is in the upper left-hand corner of the display window, and that's 0, 0. And the x-axis runs along horizontally in a positive fashion. So there's really no negative numbers that are drawn. All we can see is starts at 0 and increases this way in terms of x-coordinates. And our y-axis, and this is the part that probably will get you a little bit if you're really used to the Cartesian coordinate system, the y-axis is positive in the downward direction. So it comes down this way, positively, okay? So we can have the maximum coordinates for each of these corners, or the description of the pixels in each of these corners. Up here in the upper right corner, if the width of the screen, the display window, is held in a variable named width, since we started at 0, the x-coordinate of that position would be width minus 1. And the y-coordinate of that position is 0 because we're not off the x-axis. Likewise down here in the lower left corner, we haven't moved any to the right, so our x-coordinate is 0, but we've gone height pixels down, and since we started counting at 0, then the coordinate for that pixel down there is height minus 1. And the lower right-hand corner then would be at coordinate width -1, comma, height -1. Okay? So there is our coordinate system in processing. Every pixel in there has one of those coordinates associated with it, and that's how we know where to draw whatever it is we're going to draw. Now, the what to draw is a little bit more complicated because we have many different ways to draw things. We can draw individual pixels, we can draw lines, we can draw shapes, we can draw images, we can draw text, and other things even. So it gets a little complicated. So we're going to start simple. We're just going to talk about rectangles. So we're going to paint a rectangle, and the way we'll do that is by calling the rect method, the rectangle painting method. It's sort of like the system method calls that we use to bring up the dialog boxes in the temperature conversion example, except this method, when we call it, causes a rectangle to be drawn on the display window. So in order to make that happen, there's 4 pieces of information we need to know about the rectangle that we'd like to draw. So if this is the rectangle we're going to draw on our display window, we need to know the x and y coordinate of its upper left-hand corner. Remember our coordinate system, that's where those numbers come from. Then we need to know the width of the rectangle and the height of the rectangle. So given those 4 numbers, we can specify the kind of rectangle that we want to draw. Okay? Now that's not all we need. We need where we're going to draw, what we're going to draw, but we also need to know what color. Well, processing can specify colors in several different ways, which are called color models. We're going to use the RGBA, which stands for red, green, blue, alpha model. Okay, and in the RGBA color system, a color is mixed by adding different amounts of each of those red, green, blue components. So you vary the numbers. There's 4 numbers in a color: red, green, blue, and alpha. Vary the numbers for red, green, and blue, and you get a different color. And that number is specified as a number in 0 to 255 inclusive. Okay, so that maybe tells you that there are 8 bits in each color specification. So 0 is the least amount of the color, 255 is the maximum amount of the color. Alpha is the degree of transparency, and that's optional. You don't need to use it. It's also a number in 0 to 255. If we use 0, that means that color is completely transparent, which means it won't show up at all. And if it's 255, that means that when we draw it, it's completely opaque and nothing underneath it can be seen. If you don't specify alpha in your color model, then it defaults to opaque so that no one can see through that color. Okay, whatever was underneath it isn't drawn again. All right, so to use a color then, you need to know 4 numbers, all in 0 to 255. Thankfully, processing has a simpler way to do that. It's called the Color Selector tool, which is accessed from the menu, the Tools menu in the Processing Development environment. And when you bring up this tool, you can drag your mouse over this area, up and down on this scale to produce different colors. And then when you click on a spot in the window, the R, G, and B values will be shown there. Okay? And the color itself will pop up here so you can see a good example of it. So instead of trying to figure out colors manually by twiddling around with those different values, instead you should use your color selector and then write down those numbers and use them in your program. All right? So that pretty much wraps up this introduction to graphics in processing. What we're going to do next is move on to a video that is uses all that information to draw what's called a test pattern. So the problem statement for the example is going to be in a window with a 4:3 aspect ratio, draw a test pattern similar to the SMPTE test pattern, okay, Society of Motion Picture and Television Engineers. And in particular, what we're going to do is draw 7 equally sized vertical bars across the window. And from left to right, the colors of the bar should be white, yellow, cyan, green, magenta, red, and blue. So we actually know everything we need to know in order to do that example, because we know how to do rectangles and we know how to do colors. So that's what the example will be about. This is just to preview it for you. This is what the SMPTE test pattern would look like. Back in the olden days when TV channels used to go off the air for the night, they would broadcast something like this, just to fill the airwaves with something while they weren't broadcasting anything interesting. And ours that we're going to draw will look like this. So that's what you should look for in the next example, is the design and implementation of the test pattern sketch. See you then.